Welcome back to Teaching the Unteachables, where we dive into teaching and learning methodologies for professionals like you. This recording is from a portion of episode 73 of Did You Know the ESCO HVAC Show? Learn more at escogroup.org as well as hvacredu.net. Well, hello, everyone. Thank you for joining Did You Know, the ESCO HVAC Show. Being joined this week by Todd Kler from hvacredu.net. How's it going, Todd?
Howdy.
I thought I was going to be running on this one solo because I've got Ty, I've got Daniel, and I got Eugene all down at the symposium, down at Brian Orr Symposium in Florida. We had AHR last week, which was insane. A lot of stuff going on. So this kind of segues into what did we find at AHR, right? We found lots and lots and lots of inverters, lots of A2L. We've seen a lot of communicating equipment. And I always kind of preach about the communicating equipment. And you and I, we have some fun conversations about, what is happening in the automotive industry, especially when we talk about communication stuff, right?
Indeed.
Yeah, automotive, there was a time when every different manufacturer had their own code reader. You had to plug in and see what was going on a 5-volt DC communicating network, by the way, most of the time, right? And so when we get into talking about new technology, a lot of us are uncomfortable with communicating equipment. Now, I'm going to break this into two different types of communicating equipment. We're only going to cover one today. Hopefully, we'll get through all of it. I've got a ton of stuff for us to talk about. Today, we're going to talk about unitary communicating, and we're going to talk about all of the different manufacturers and how they really are on the same platform and how to test those platforms, how to see when you have problems on a network. And then on another episode, we're going to talk about our, let's call it ductless communicating, our higher DC voltage communicating platform. So, Todd, you spent a lot of time in the BEAS side of things, building automations, and you guys have got a great course over at HVACR EDU. And so BAS and our unitary communicating really are very similar.
The 6 1 half dozen the other, right? I mean, they're very similar the way they communicate. It's going to be a DC voltage, right? Usually a 5-volt DC. Very, very, very similar to a pulse width modulation. We may have heard that in the industry, right?
Absolutely.
And so that communication here, we have a master slave type application, and this is very similar to the RS-85 cabling that we are used to. Usually a four wire lead wire, and usually 2 communication and
That's
two or one for voltage to power to the device, usually 12 volts, maybe sometimes 24, depending on the device.
Exactly.
And then a common, right? You got to make that complete circuit.
So when we look at that communicating platform, this is very important for people to understand that we're going to look at all these different manufacturers and you're going to see a similarity. You're going to see in a lot of these a 4-wire system, 2 that we're going to communicate on and 2 that we're going to supply power. Now, we do get into some differences in the way we communicate, but it is all very much the same. So if we look at this basic layout of what we call an RJ45 communication, so where we're talking about like Cat6 cables or when we're looking at communication cables, a lot of different industries use a same or similar platform. So even our Ethernet cables, we're using a variable 5-volt DC. It's a 0.25, but it's plus or minus. And I'll show you what that looks like here in just a second, how we get to that. But we've got some supply voltages and we got some communicating voltages. And we're going to go through all of our manufacturers here. And there are some that are better at giving information into it and then some that are not. So Todd, you want to break down just a little bit about how some of the decoding side?
Yeah, so most of us, at least in the residential or unitary type split systems, are accustomed to 24 volt, right? Yeah. Our thermostat, in a 24 volt system, we have a thermostat. In a communicating system, it's no longer a thermostat, it's now a control or a controller, right? Yeah. And the 24 volt system, it's just the thermostat is just a fancy switch, and it sends. It's gonna
like a light switch.
It's gonna be a light switch, right? But in this case, 24 volts typically. And in doing so, we either tell the heat to come on, or we tell the compressor to come on. Sometimes, in some cases, 2-speed, right? We have a 2-speed condenser, right? It's still not communicating. Okay, but when we dive down that communicating, where usually we get that 4-wire, 2 communicating and two other 24 volt or 12 volt, depending on the manufacturer, and a common, right? So there's your 4. That DC voltage is usually 5-ish volts, and it'll pulse width, right? So it'll on
Some
Exactly. The
modulation there.
voltage come on for a half a second, millisecond, and go off. And that language, or how long it stays on or off, is interpreted by a language and usually a protocol.
Hmm.
And that protocol will speak to that controller or module or the PC board that it's communicating with. Inputs, outputs, right? We're going to get those signals from thermistors, pressure transducers. It's going to say, hey, at this pressure, at this temperature, do this, or hey, do this when you get to these pressures or temperatures or whatever it might be.
And we do it in those pulses, and that's the important part to understand. Remember that AC was just a simple command, 24 volt, on or off. Well, we're now going to do this in pulses that are going to be on or off.
Time.
But the amount of time that we are on and the amount of time that we're off are going to be the language that we're speaking. And many of our different manufacturers use different languages. We're really just talking about different spacings within the
Ones and zeros.
modulation, right? And we can, yeah, it's all ones and zeros. And we can actually read that. Now, we're not going to go this deep on it. We're not going to bring it on oscilloscope, although maybe down the road we'll do this so we can actually talk about it a little bit. So if we were to put an oscilloscope on a communicating network, we're actually going to see our ones and zeros, but we're also going to see those as a positive reference to ground and as a negative reference to ground. We're actually going to go both directions because they came from our AC sine wave. So the important thing to remember is all of these DC communicating voltages started with our 24 volt AC power supply. So where do our DC circuits begin? Typically, it starts at our indoor unit. For residential unitary split systems, it starts at our furnace or our air handler, where our original power supply was at. So we'll take that AC voltage, we'll turn it into the DC voltage, and then we will start pulsing that thing.
Yeah, you made mention that we get that transformer of 24 volts from our indoor unit. Do keep in mind this is unitary, usually a split system. Now, when we do go and talk about ductless split system, then it's coming from the outdoor unit. So just keep that in mind. Everyone's going, hey, time out. That comes from the outdoor unit. Yeah, in a ductless system.
Exactly. And our inverters that have a power supply at the outdoor unit, they will typically have their own as well. And we'll show you a little bit on that, what that one is. So for those that are comfortable with the Daikin platform or the earlier Goodman Amana stuff that was using the Climate Talk platform, let's look at this real quick. Remember those 4 wires,
Yes,
Todd? What we're going to use in this particular platform, we're actually going to use 2 of those for 24 volt AC. So that great big colorful screen that we have on our thermostat, right? We still need to light up. If we put batteries in it, we know what's going to happen. That we had seen that back in the early 2000s when you put batteries in a digital thermostat, you burn them up. So we're actually going to use 2 of those for 24 volts AC, R and C, just like normal. And that common is actually very important. It is a reference to remember what we do with the 24 volt side of the transformer? We ground it, right? So
we have to.
We have to. So on a grounded transformer, our common is actually connected to ground. This is very important when we start looking at and testing the communication. If we look at this communication, so we're going to run 4 wires from the thermostat to the indoor unit, and depending if we're talking about like the FIT system uses a electronic expansion valve, we've got a board on that as well. So we're going to use AC for powering our controls. We're going to use our communicating the 2 wires. They're going to do this on number 1 and number 2. And so they're going to supply 2 wires to the outdoor unit. And when we're using a communicating outdoor unit, the board of the outdoor unit actually has a power supply built on it. So we're not going to be connecting R and C. We're just supplying the 2 wires. But if we have a bad ground within the system, we can really have some issues. And I'll talk about that here in a minute once we get a little deeper into what's going on with these wires. It'll make so much more sense. So what are we actually doing to get those DC signals? Well, with this particular platform and with many of them, when we take our AC sine wave, we actually, because we have a grounded circuit, we have a reference point. And so now we'll actually utilize the voltages that are above neutral or ground and the voltages below. So we're going to have one signal that's in positive reference to ground and one signal that is in negative reference to ground. And that is the number 1 and number 2 wires. So when we use our circuit to be able to rectify our AC, we're going to get a DC looking signal because it's going to be chopped off. And now we're going to do these pulses within it. Think about it as like SOS, inside of that wavelength, right?
That's a great way to explain it. It is your Morse code, right?
All it is. Just our spacing, our timing is all we're actually doing.
And that zero voltage baseline. I don't know if y'all remember, maybe in some of the furnaces you plug in, and if you have a 2-prong and you don't have that ground, and then all of a sudden your PC board doesn't work.
It doesn't like it.
Because it has no reference to ground.
No reference point for our voltage. So those two wires have a reference to ground. That number 1 and number 2 have a reference to ground. And there's a difference between the two of them that we're going to call the bias. So with this particular system, this climate talk system that we're using with Daikin and some of the earlier Goodman Amana stuff, we are going to be able to measure from ground to number 1 and from ground to number 2 and get 2 different voltages. And what a lot of people don't realize is that difference between them, that bias, is actually our bandwidth. So about a year ago, I did a class with John Brown over at EWC where we went really deep into this exactly. So if you want to learn more about that, on this finished edited video, I'll make sure to put a reference to get back to that one so you can understand what that entire bandwidth looks like, how to set the bias, if your bandwidth's not good, how you adjust that. But for today, we're not going to go that deep. I just want you to understand when you're looking at that, we actually have those signals above ground and below ground in reference, right? Mm-hmm. So some positive, some that are actually negative. So if we were having a problem on a communicating system on the Climate Talk network, we could actually take our meter and we could measure from common over to number 1. And we should be reading a positive 2.8 volts DC. There is a difference when we have an air handler. It only uses 3 volts DC. And we can actually talk about that. If they're really interested, I can show you the math on how to figure out the bias on an air handler that's using 3 volts DC and 5 volts DC. It's simple. You take the 2 that are on number 1, you add them, divide it by in half. Take the 2 for number 2, add them, divide it in half. And so the difference between those should still be that 0.6 volts DC or greater. Now, if we took our meter and we went from common to number 2, we're going to see that we're going to have that 2.2 volts DC. It's a negative, right? So we have a positive and then a negative voltage gives us a bias of 0.6 volts. Here's the thing. If we do not have 0.6 volts DC bias or greater on the Climate Talk network, you're coming back. It's that simple. It really is. You can literally measure between number 1 and number 2, and if you have less than 0.6 volts DC on a Climate Talk network, you do not have a stable bandwidth. You have conductors that are corroded because a mouse has chewed on them. You have conductors that have kinked or broken. You have conductors that are not landed properly on the terminals. You have wire nuts sitting outside from your existing solid wire that got water in them that corroded and no longer allow the communicating voltage because we don't have the amount of current that we had with AC. It's very, very, very low current. So it's super simple to check the bandwidth. So if I'm an educator, I'm bringing in a new Daikin communicating system, I'm connecting it, I actually can now show my students how to make sure that my network is good and operating properly. If it's not, this is where you start. You start on the bias voltages. So if I am trying to isolate a system, say I've got all these components hooked up. This particular one, I got my thermostat, I got my indoor furnace, I got my cased coil, and I got my outdoor unit. If I am struggling for communication, I just start it. Where would I start, Todd? Where does my DC voltage begin?
It's going to be at the ground. You got to get a reference point.
Got to get a reference point of ground and power at our indoor unit. Yes. So worst case scenario, disconnect all your wiring. Check it. Make sure we got our 2.8, 2.2, or our 0.6 bias difference at our indoor unit. It's going to be 1.9 and 1.3 on an air handler, but it's still a 0.6 difference. And then start adding my parts. When I add something on and my voltage bias changes, guess what?
0.6.
If it's not, I've just found my problem.
Yes.
Now, I will talk about one really oddball one that I have found. And after I found it, it made sense. Look at that outdoor unit. I got 2 wires, right, going to the outdoor unit. So I'm communicating my DC voltages. So where is my reference point, Todd?
From the indoor to outdoor?
Yeah, there's no wire. Where would my outdoor unit find as a reference to ground?
Well, it is connected to hopefully a disconnect. That disconnect hopefully is grounded. So
Back to
we
the
got
same
equipment ground
electrical
back
panel.
to
Exactly.
the
All right.
panel.
Yeah. So I had a technician that called me and said, "Hey, I've got good bias voltage at my indoor, at my thermostat, and my EEV, my outdoor unit. I've got some janky voltages and my bias is not right." I'm like, "Well, that's really interesting. Let's check your voltages to ground," and check the voltages to ground, and they were low at the outdoor unit. So I had him disconnect the wires from the outdoor unit, check the wires going to the outdoor unit. The wires were good. So as soon as we connected it to the outdoor unit, the voltage dropped. And I thought, well, maybe it's a board, or is there something else? I thought, well, let's go check all of our ground. And we found a corroded lug inside of the disconnect that had poor connection. So the path could not make it back through the electrical panel to the indoor unit. The reference point was bad. Clean the wire.
And I've seen on rare occasions, probably a handful of times, maybe half a dozen times throughout my career, the UFER, the residential or even commercial, the UFER it got corroded, got water on it, and that UFER, that reference ground, that rod that goes 6-8 feet in the ground, was corroded.
Yeah, absolutely. Remember on that AC system that was using 24 volts AC to run a contactor, it didn't care. It had enough AC voltage running to the compressor. Probably may not have been the safest thing in the world, but it didn't affect the way that our 24 volts AC operated contactor, but could absolutely with the communicating system. So I have had incidents where I had bad ground wiring that was not able to be reconnected properly. And so we would simply connect common from the indoor to common of the outdoor. Cannot use R because we already have a power supply at the outdoor unit on those, but we could use common as a backup. Okay, so that's an overview of our Daikin. We learn a lot about what's going on, in that one. So let's look at the other networks and see how similar they are. Now, we'll see one in the JCI side. A lot of times you'll see it referenced as Echelon. It really is their communicating system. Yeah, I see two primary connections because they've had a couple different generations of it, right? So you'll see one that is labeled ARCB, primarily using green, red, black, and blue or white wires. And then you can also see a variation of that is just common, B, and A. And I like finding this one in their service manuals. Remember, almost all this comes right out of the service manuals. This is not like hidden stuff. You have to read it to find it. But it's in there.
You have to read?
You have to read, right? That ground rod is absolutely. And we got places out west that don't have ground rods. They have, ground arrays where they have shallow, wide grounding. But it is absolutely in a dry condition, and it becomes less of a conductor. So it's very important to understand that ground is part of our communicating network. We didn't think about that before, but it is now. So let's look at this JCI one, and we'll see that either way you look at it, we've still got a common. We have A, which is our positive reference, and B, which is a negative reference. If we go back to the other diagram, which is their newer design, we still have R, we still have common. You just have B on the end and A on the end.
You got what? A positive and B negative. Gee, I wonder which one those are without even referencing what A and B are.
Isn't it? It's amazing when you look at this from the perspective, because remember, a lot of us, I would say most of us educators, we're technicians out in the field, many of which never worked on communicating systems. And so sometimes we're a little leery to bring communicating systems into the classroom because we don't completely understand them. Well, you get done with this class, you're going to go, that's all? Bring it on, because I've got this. This all makes sense. Everyone's really doing this, and they're just saying it's different. Yeah, pretty much.
It's just a different. It just matters a different protocol, a different language.
Exactly.
But it's being delivered to one piece or one controller or the unitary devices in the same way, just a different language itself.
Different language. Now, I will say that I cannot speak for the bias voltage between 1 and 2 for the rest of the manufacturers. I know the Climate Talk pretty well, and there's a lot of training material for that. So if there's anyone out there that has tested the bias voltages and know more about the bias voltages between different manufacturers, I'd love for you to hop on, because that's a piece that not every manufacturer likes for you
to disclose either.
To disclose, right. So I'm curious myself, but I mean, I've got my own ideas. But let's talk about how do you check these, okay? So if we're talking about this particular network, So with this particular one, so if you think there's a communication issue, you're being told in the service manual to isolate A plus and B negative, right? And then measure the A plus and B terminals to what? Common.
To common. To a reference point.
Back to our reference point of common once again. And so this particular one is done a little bit different because they are utilizing voltages at each different part. And so they're saying, all right, let's just make sure that if we're going from A to C isolated, that we're going to have 3.2 volts, and B to C is going to be less than a volt DC. Right? So it's really communicating positive from A to common. At the indoor unit, we're checking A to common, we're checking B to common, outdoor unit, A to common, and B to common. And if you look at it, it's simply stating we've got a 3-volt DC power supply on these instead of a 5-volt DC power supply.
And each manufacturer will be different.
That's right. But
it goes back to that protocol language.
It does. How do we check them? We simply open up the service manual and verify the voltage. You're going to find that some of these look really similar to each other when we get into it. All right, so let's take a look at the infinity line. Most people are comfortable with infinity. I have a lot of people go, man, I really struggle with my communication line, especially if I get into zone systems. And I'm like, well, let's just understand what we're doing on that zone system. Let's look at the entire system. What is infinity? It's 4 wires, okay? And they are going to be labeled A, B, C, and D. Now, if I were just a guessing guy, Todd, and if I didn't go into the next slide we're getting ready to look at, I might look at that and go, I got 2 wires going to my outdoor unit. I wonder what's on those 2 wires.
Gee, I wonder. Well, if it's the outdoor unit, it probably has its own. If it's communicating, it probably has its own transformer.
Right.
Well, we aren't going to have. We usually don't have common hooked up.
Right.
Rarely ever, unless we have a problem like you described.
Exactly.
We're not going to have R hooked up.
Right.
So the only other 2 wires there, in this case, green and yellow. One's got to be a positive DC and one's got to be a negative DC.
All right. And then from my indoor unit to my thermostat or whatever I got 4 wires. So let's take a look and see what those actually are. Well, look at there. So you got to break it down a little bit different from this manufacturer, but let's start at the very bottom. And either one. Let's just start at the top. Okay. And if we go from C to D, well, that looks awfully hot to me.
That looks awfully familiar.
That looks like an R to me. And they're all in reference. A, B, and C are in reference to C. A and B are both in reference to C, and D is in reference to C. So C must be common. So C is actually common, and D is actually 24 volts hot. And A to common, I'm going to have a 3-volt DC signal. And B to common, I'm going to have that 0.1 to 0.3 volts DC.
And of course, that little tilde is approximately 3 volts, approximately 0.01 volts.
Exactly. And so they are showing you to reference it a little bit differently. They're saying, hey, on the top reading with the board power applied, so I got power going to the board, but no units connected. This is the voltage you're going to see coming from the indoor unit. And then once I connect things, I'm going to see a change in voltage, and I'm going to see it moving between 2.5 and 3.9 volts DC. And so that is how you test that communicating network on our Infinity system. Let's just keep on going.
And anything outside those parameters, we got a problem.
You got a problem between them.
If I look at and it's usually, typically, your wiring.
Absolutely.
It's usually not the controller. It's usually not the board.
Yep. The only thing that I don't see in many of these, except for the very first one, is measured between A and B, which that would be our bias voltage. So I need to round up some is what I need to do. I need to get in some of my friends' labs and go, all right, what's the bias voltage on every one of these manufacturers? Because I got a feeling they all operate under the same principle that if I have a certain bias, then if it's below this, I can't communicate well.
So what are we looking at here?
All right, let's take a look at Linux iComfort system, right? Woo! I like those. Good pieces of equipment. What do they do? Wow. They get kind of crazy with the wiring diagrams. Let's stare at this for a minute and go, man, am I really going to work on this thing? Yeah, you are. Let's break it down a little bit simpler. We can look at this one, or we can look at the one after it from another piece, and it sometimes makes it a little easier to understand what those 4 are doing. All right? Let's start at the indoor unit, Todd.
All right, let's go to the indoor unit. And interesting that everything's tied back to the indoor unit on these unitary.
Yeah.
It'll be completely opposite when we get to our ductless.
The ductless, absolutely. But all of our unitary, our primary DC voltage is coming from that indoor control board.
Yes.
So let's look at this indoor control board. This one's using a smart hub because it's connecting another component to it. But we can even talk about the smart hub if we needed to. But what do you see at that indoor unit? Do you see 4 wires?
Yeah, I do. I got an R, I don't see at a common. So the R in the common, I imagine, be 24 volts, and the 2 in the middle, I see a negative and a positive. I can't read what they are.
They call it I, but it's I positive and I negative.
So there you go. I wonder what those are.
Right. So as elusive as these may seem, they're really not. One difference that we do see with this particular brand is we may not be using that 24 volt AC all the time. We might have a 12 volt DC. So if we hop over to the smart hub up here, when we get to our smart hub, we originated with 24 volts AC and our 2 communicating. When we go out of our smart hub, we're actually going to now start using a DC voltage to work with, but we still have our A and B, or positive and so let's jump over to some of our ICP products, right?
Gee, I wonder if this is going to be similar to Carrier.
Kind of looks a little similar. Now, they've had 2 different generations too, though. So you're going to see Observer, you're going to see Ion, and I'm going to show you a couple different wiring diagrams, but let's break it down, right? Let's put it into perspective.
Looks pretty similar.
What do you see there, Todd?
A DX positive, or DX negative. I wonder which ones those are. Data?
Right. In our indoor unit, it might call them A, B, C, and D, but then all we got to do is we got to look at the wall controller, or we look at the outdoor unit, and we see exactly what those things are. So I see 24 volt hot between common and D or R. And then I see a negative communicating signal on B or DX negative and a positive on A. Looks pretty dang familiar. I wonder if we can check this one. Well, why not?
Look at that.
So,
geez, doesn't that look similar to what
I'm not even going to go there. Wait, we name throw.
Yeah, I wonder why.
Well, we're just saying that their training material on their slides look similar. That's all we'll say. So yes, DX negative to common. That is common. Commodore 24 volts. So we're just on 3 volt DC. We're going to see 3 volts on both of them. And if we don't, we got to disconnect. And we got to start seeing where we're losing it. So the best way on any communicating system, disconnect your control wires, start at that indoor unit, verify you got good voltage coming from it, and then start adding them one at a time. Let's look at Comfort Sync, right? Let's look something.
You think this might look similar to Linux?
Well, look at that. I'm seeing common, I'm seeing R, I'm seeing positive, and I'm seeing negative again.
And look at our pseudo shielded cable with our typical 18 gauge whatever.
Yeah. So if it's a non-communicating wire, we got communicating existing wires. Boom. We're going to tie those together. And then we're going to check our voltages, right? So it's the service instructions are a tad bit different.
They're a bit different.
But, this is because of the communicating platform that they're using. What we're checking changes. How we check it never actually changes. So we know that it's a 5 volt DC system, right?
Yep.
So we can now check the pin 1 to pin 2. We should have 4.5 to 5.5 volts DC when it's not communicating. So when it's sitting there idle. Pin 3 to pin 2 should read 4.5 to 5.5 when it's not communicating. And then pin 2 to pin 4 should read 4.5 to 5.5 volts DC.
Geez, they all look like 4.5 to 5.5.
I'm telling you. That's why I like doing this class. Because when you go through it all and you go, oh, really? Oh, this all makes sense now.
One last thing I'll put in there is that communication systems are here to stay.
They are. And we're going to be
not going anywhere.
And more and more. And hopefully we'll end up persuading a common
language, common protocol,
common platform. All right, Todd, once again, always fun hanging out with you, my friend. I love these conversations, and it's just about bringing quality education to the industry. So,
yeah. And one final, before we say goodbye.
Yeah.
Happy birthday to my best friend Clifton.
Woo! Thank you, everyone. You know what?
All right.
I had people saying, what kind of glitter are you wearing today? And I was like, I don't want to do this the whole time, but
how come you don't have your get up from AHR?
We just picked it up from the dry cleaner, so got prepared for our conference.
There you go.
All right, everyone. Thank you so much for joining us once again. We'll see you all next week on Did You Know? The ESCO HVAC Show. Bye.
Bye-bye now.